In this problem, we're given an array f0 to n of integer, where n is greater than 0, and we're asked to find the index of the largest value. So before we begin, let's go over the question and underline the important bits. Okay, we're dealing with an array. The array is an integer array, and we're told that the dimension of the array is n greater than 0. And we're asked to find the index of the largest element in the array, or the largest value in the array. So n greater than 0 means that the array will contain at least one element. It can't be empty. And that's because we're looking for the index of the largest element. If it's an empty array, we can't find the index of the largest element. There's got to be something in there. And remember, we're finding the index of the largest element, or the largest value. We're not looking for the actual largest value. We want its index. So let's write down our specification. We'll have con n of type int, and that will be n greater than 0, and that comes from the question itself. We have f is the array, and that is from 0 to n, and the type of the array is an integer array. Next, we'll need some variables. So what variables do we need? Well, we're looking for the index, trying to find the index of the largest value. And an index is a number, so we'll need some kind of variable that gives us an index or a number. So I'm going to introduce t, and that's going to be of type int. Then we'll have the label s, which represents our program, and we'll have to write down our post condition. So if t is an index into the array, then t must have a valid range. So as part of our post condition, we'll give t a valid range. So t will be greater than or equal to 0 and less than n. And the next bit of our post condition will tell us what the program is actually going to do. So we'll say for all I greater than or equal to 0, less than n, and we'll say f dot t is going to be greater than or equal to f dot I. Now, why are we saying f dot t greater than or equal to f dot I? Well, if the program s has done its job, t will equal the index of the largest value. So if t is equal to the index of the largest value, then f dot t will be greater than or equal to all the other values in the array, f dot I. And that's our program specification. The next thing we need to do is we need to write down an invariant. So to get our invariant, what we're going to do is we're going to replace a constant with a variable. And for our purpose, we're going to take n and we're going to replace that with small n. So wherever there's an n, we're going to take that and replace it with a small n. So to write down our invariant, we're going to say P0 will become t greater than or equal to 0, less than small n, and for all I I will be greater than or equal to 0 and less than small n, and we'll still have f dot t greater than or equal to f dot I. And of course, because we've introduced a new variable, essentially this new small n, we'll have to give that a range as well, and that becomes p1. So the values that n, small n, can have are, it can be greater than or equal to 0 and less than or equal to large n. Now it's important to note that small n must be allowed to be equal to large n, because effectively this isn't a range, this isn't an index really, a range for an index. This is our invariant, and n will start off at 0 and work its way towards large n, and when it meets large n, or when it's equal to large n, our loop and our program will effectively finish. So if we didn't allow small n to be equal to large n, our program would not finish or wouldn't terminate. And we'll actually see that when we come to write down our outline solution and our guard and loop. So our outline solution then takes our invariants P0 and P1, and we write down an outline solution to give us some idea of what we need to do. So to start off with our outline solution, we're going to say that we're going to have S0, which is basically going to look after initializing our variables. And once we've initialized our variables, that will establish our invariant P. Now, because we've replaced large n with small n, our bound function will then be large n minus small n. Our loop then becomes do small n not equal to large n. And how do we know that this is the case? Well, effectively, because we've replaced large n with small n, we know that we're processing the array in this direction. We have 0 at this end and we have large n at that end. So because we're processing the array from left to right, that means that at some point small n will reach large n. So we should loop until small n is equal to large n. The bound function n minus small n is correct because n is a constant, it remains stationary, and if n starts at 0 and moves its way up towards large n, we should get a decreasing function, but we'll prove that in program termination. So inside our loop, what we will have is our invariant P, and we'll know that small n is not equal to large n. Then in the loop body we'll have S1, and then after S1 executes, the only thing we know to be sure at that point is that our invariant should still hold true. The loop will finish, and at that point we should have our invariant P and small n will equal large n, because the loop will have terminated and finished, and that should give us back our original post condition. Because small n will be equal to large n, so we can substitute back in large n. So the first thing we need to do is initialize our variables, and that is S0. And then we'll move on to look at what needs to happen in the loop body at S1. So S0, initializing our variables. If we consider the problem, what we need to do is find the largest element in the array and then figure out what index it's positioned at. So if we look at this sample array, we'll see that it's really just a comparison problem. We need to compare one element against its neighboring element and look for the largest, store it, and move on. So by keeping track of the largest element so far in the array, we'll then be able to figure out what index it's at. So if we look at this array, the largest element in the array is 10, and clearly its index is 3. So really what we need to do is follow the same line of thought that we have for finding the largest value in an array, except don't store the value, store its index. So then really the problem is a comparison problem. And in comparison problems, we need to compare pairs of elements. So we'll look at F0 to begin with and F1, compare them, see which is the largest, store it, its index value, and move on and compare the next pair and the next pair, and so on and so on. So to do that, we cannot, for example, say that n and t become equal to 0 and 0, because then we'll be comparing f dot 0 with f dot 0. So that comparison won't work. We'll be comparing an element with itself, and we can't do that. So to solve the problem, what we're going to do is we will offset n into the array. So effectively what we'll do is we'll set t equal to 0 and n equal to 1. And that way we'll have a comparison of f dot 0 greater than or equal to f dot 1. If we look at this little sample array up here. So that would be our first comparison. And then we'll increment n and move on and continue to compare pairs of elements, or compare f dot t with f dot 1, f dot 2, f dot 3, f dot 4, and so on. So what we really need to do for our initialization is to suggest that n comma t becomes equal to 1 comma 0. And we'll have to substitute those values in to both P0 and P1. So just to get it out of the way, what we'll actually do now is we'll take P1 and substitute that into P1. So P1 is n greater than or equal to 0, less than or equal to large N. So there's only n in here, not t. There's no t in this part of our invariant, the P1 part. So we'll just substitute in n becomes equal to 1. So through substitution, we'll end up with 0. And then n gets replaced with 1, so it will be 1 greater than or equal to 0, less than or equal to large N. And what we'll do here is we'll break this down by using excluded middle. and that will become 1 greater than 0, greater than or equal to 0, and 1 less than or equal to n. Of course, 1 greater than or equal to 0, well, by arithmetic we know that that's true, so that will be true, and 1 less than or equal to n. Now this basically will all end up being true, because we'll have, by the laws of constants, we'll end up with true and anything. Well, that just leaves us with the 1 less than or equal to n, and that follows from what we were given, because we're told that n is greater than 0 at the beginning of the program, and of course n greater than or equal to 1 is the same as n greater than 0, because the smallest value n can have under n greater than 0 is 1 or greater, and this is essentially the same thing. So P0, the P0 part of our invariant, works out with n equal to 1. So next we move on to the P0 part of our invariant, and again what we're doing here is we're substituting in, and we're suggesting again that n comma t becomes equal to 1 comma 0, except we're taking the whole P0 part now and substituting that in. So let's do that. So we'll have 0 and t less than, and we're substituting in, well actually let's write it out first and then do the substitution. So we'll have, for all I greater than or equal to 0, less than n, f dot t, and of course f dot t is greater than or equal to f dot I, and we will substitute in n comma t becomes equal to 1 comma 0. So through substitution we get 0, and t is going to become 0, and n is going to become 1, and we have for all I, and I is going to be greater than or equal to 0, less than the n, and the n is going to become 1, and we have f dot t. Now remember, t is going to become 0, greater than or equal to f dot I. There's no substitution for I, so that stays the same. Once we have that, we can now look at the range for I. And when we inspect the range for I, we'll see that I is greater than or equal to 0 and less than 1. So the only possible value I can have within that range is 0. It's not an empty range, it's a range of a singular value for I. Now because that's the case, all of this now becomes very easy to simplify, because we can say that I is effectively equal to 0, so therefore we end up with and all of this piece, the for all I greater than or equal to 0, less than 1, f dot 0 greater than or equal to f dot I, simply becomes f dot 0 greater than or equal to f dot 0. Because I is 0, so the only value that I can have is 0, and effectively all of this simplifies down to that simple expression, f dot 0 greater than or equal to f dot 0. So when we look at what we've got left, we've got 0 greater than or equal to 0 and 0 less than 1. So all of that's going to effectively come out as true. And then we have f dot 0 greater than or equal to f dot 0, and that's effectively going to come out as true. And this is using a number of different rules. So we'll just say excluded middle, and by arithmetic we know that those f dot zeros are the same thing. So we'll end up with true and true. Of course, under the laws of constants, true and true is true. So we end up with true for P0. So we now know that our suggestion of saying that n is equal to 1 and t becomes equal to 0 for initialization will work out. So next of all, we need to look at the loop body, S1. Now for S1, if we consider what we've just done, from S0 we know that t is going to equal 0 and n will equal 1. And we know that the guard on our loop is n not equal to large N. So n will move from left to right and progress up towards n, large N. In order to do that, it's got to be incremented. So n needs to become equal to n plus 1 in order to make progress. So we'll suggest that n becomes equal to n plus 1 for the loop body. And this time we only take the P0 part of our invariant. So we'll say t greater than or equal to 0 less than small n, and for all I greater than or equal to 0 less than small n, f dot t greater than or equal to f dot I, and we will substitute in n becomes equal to n plus 1 in order to make progress. So through substitution, we'll end up with 0 and t greater than or equal to 0 less than n plus 1, and for all I greater than 0 and less than n plus 1, f dot t greater than or equal to f dot I. Once we get to this point, we need to look at the n plus 1 pieces. N plus 1, and we have n plus 1 here. So we need to then look at the split off rule, and we need to split off what we've previously processed and what we have left to process. So the split off rule comes into play here. So we'll split off I equal to n. So if we look at an example array here, so what we're really saying is that, okay, this is 0, this is n, and this is small n. And this is what we're currently looking at here. That's the element that we're currently processing. Now I, in this range, where I is greater than or equal to 0 and less than n, that's what we've previously processed. So all of that has been previously processed, and this is what we're currently processing. Now everything in this range, where I is greater than or equal to 0 and less than n, our answer from this part of the array that we've previously processed will be stored in t, because t will be equal to the largest element, or the index of the largest element so far in that range. So t will be equal to the index of the largest element in this range that we've previously processed, and this is what we're currently processing. So our focus then comes on to f.t greater than or equal to f.i, and in this case we're really processing this part, the f.i bit, and the I will be replaced with n, and we can really just say everything else that we've have on this side is what we've previously processed, which will in fact be stored in t. So what we'll end up with here is our split off rule. So let's just make a bit of room to write that in. Okay, so we will really just be rewriting out what we have above and chopping off the plus 1 bit. So we'll say for all I, and then we'll have I less than n, and in this part it will remain f.t greater than or equal to f.i. So all of this is the bit that gets split off. This is what we've previously processed. So t will hold the index of the largest element in that part, and because we're dealing with a for all, and we know that for all gives us a conjunction, the split off becomes and f dot t greater than or equal to f, and not f dot I but f dot n, because this is the bit that we're currently processing, this is a bit that we've previously processed. So then that really follows from our invariant. If we follow the logic of our invariant, all of this in the brackets is what we've previously processed, which is stored in t, the index of the largest element so far. And we're going to compare what we have so far with f.n. So therefore what we're left with is f.t greater than or equal to f.n. At this point we can't simplify this down any further. There's nothing we can do here because we don't know what f.t is and we don't know what f.n is, so we have no way of evaluating this expression because we don't know their values. So all we can really do at this point is to use case analysis. And case analysis will allow us to query or to look at the possibilities of what f.n could be, and then write down the outcomes based on those possibilities. So the next part of deriving the loop body will be to use case analysis on this expression. So when we look at case analysis, we're interested in f.t greater than or equal to f.n. And if we consider an example array over here, let's say we've processed the first 3 elements already. So in this case, if we processed up to here, up to n, then f.t should be equal to 10, because t should be equal to the index of the largest element so far, which is, in this case, 1. So f.t is essentially saying f.1, and of course that's equal to 10, which is the element or the value of the element at that position. So that's what we've done so far. Now if we're processing at n here, and let's say n is equal to the value 11. Well, 11 is greater than 10. We found a new highest value in the array. So f.t needs to change, or t needs to change, because it's a bigger value at f.n. So we'd really like to change f.t, or t, to no longer be 1 and to be now equal to 3, because 3 is the new highest or new largest value in the array. So this is really the comparison that we're making. So when we look at our case analysis over here, what we'll do is we'll say, okay, let's go through case analysis. And we look at the various cases. How many are there? Well, there are 2, because f.t will either be greater than or equal to f.n, or f.t will be smaller than f.n. So the first case, what do we need to do to t? Well, t will be equal to t. In other words, it won't change. If f.t is greater than or equal to f.n. So if f.t is greater than or equal to f.n, there's no need to change. We keep t as it is. The other possibility is t will need to become equal to n if f.t is less than f.n. So if we have an f.n that is greater than f.t, we found the new largest value in the array, just like we have up here. We did have 10 as the largest, now 11 is the largest. The index 1 was the index of the largest up to this point, but now we found the new largest, so now the index should be set to 3. So if we find an f.n that is larger than f.t, then t needs to become equal to n in order to store the index of that new largest value in the array. So once we've written our case analysis, we can then write our if statement. So we can translate that into an if. So we'll say if f.t is greater than or equal to f.n, well then nothing changes. So we can say skip. Else f.t is less than f.n. Well, now we do want to make a change and we want to say t becomes equal to n, and the if statement finishes, and that is it. So S1 effectively now becomes the if statement and of course the n becomes equal to n plus 1 part that actually got us here in the first place. So that's our loop body. The next thing we need to do is look at program termination. So for program termination, there are 2 parts. We need to first of all look at the initialization of n, and we need to look at what happens to n in the loop body. So remember, the guard on the loop is do small n not equal to large n. So that's what's driving the whole process. T is just a variable that we set from time to time, whereas n is the variable that drives the loop. So this is where we really need to concentrate for proving termination. And of course, always remember that for initialization, this greater than or equal to or greater than 0 bit comes from the fact that we were told at the beginning of the program that n was greater than 0. So we always include that extra bit, the greater than 0 bit, in here for initialization. So if we substitute our initial value for n in here, we'll get, through substitution, we get n minus, and n becomes equal to 1, greater than 0. Using a little bit of algebra or arithmetic, we transfer the n across the sign, and we end up with n is greater than 1. So minus 1 goes across and becomes plus 1. So we end up with n greater than 1. And if n is greater than 1, then what we originally said about n greater than 0, follows from that. If n is greater than 1, then n is greater than 0. So that works. Next of all, we need to focus on making progress in the loop body. So we substitute n becomes equal to n plus 1 into our bound function. And again, through substitution, we get n minus, and n becomes equal to n plus 1. It's easy to just bracket this off and put in n plus 1. And then we can say, by arithmetic, that that is equal to saying n minus 1. And of course, to prove that it's a decreasing function, that's always going to be less than n minus n. So our bound function is decreasing all the time. Every time around, we're taking another one off and another one off, thereby decreasing the amount of space that we've got left to process. All that's left to do now is to write out our complete solution. So our complete solution is going to look like this. Most of the complete solution, at least the first part, is exactly the same as our program specification. So it's just a matter of rewriting that out. So of course f is an array, 0 to n of int, and then we have our variables. Now remember, we did have t, but we've also now got an n, and they are of type int. We initialize those, so we say t comma n becomes equal to, well, t became equal to 0 and n became equal to 1. And then we have our loop, so we say do n not equal to n, and we have our if statement. If f.t is greater than or equal to f.n, then we skip. Else f.t less than f.n, then we say t becomes equal to n, and that's the end of our if. And of course, don't forget n becomes equal to n plus 1 every time around the loop, and that's the end of our loop. And that gives us, well, after that, small n, of course, will be equal to large N. So that ends up giving us our post condition, which was t greater than or equal to 0, less than n, and for all I greater than or equal to 0, less than n, and hopefully if everything has worked out, f.t will be greater than or equal to all the other elements in the array f.I, and that's the end of our program. So there's our complete solution with all of the various bits that we derived, and the bits that we filled in really are S0, and then of course we filled in the loop body S1, and that's our complete solution.